This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations for the Satellite Book Club Seminar Series. This is session number 24. Thank you for joining us. I hope you're staying well today. We've got a great presentation from Dr. Mike Pavolonis, who's a physical scientist at NESDIS, and he's going to be talking about the Volcanic Cloud Analysis Toolkit, also known as VOLCAT. Just a few announcements before we get started. A reminder that this session is being recorded, so your colleagues that are working shift or off today can hop on the VLab and watch this presentation later. We will have an opportunity for Q&A after the presentation. So please go ahead and put your questions in the chat room while Mike's presenting, and we'll make sure we field them through there. This week, the Q&A and discussion after the presentation is going to be facilitated by Steve Silverberg, meteorologist at the Aviation Weather Center Aviation Support Branch. We are always looking for future presenters, so if you have an application of satellite data that would help field operations, please get in touch with us. And if you're looking for training materials, whether they are not available or you just don't know where to find them, please get in touch with Brian Mata, Office of the Chief Learning Officer. His team can help with that. We, of course, thank the Tower S team, David Blutis and Lee Byerly, for their help arranging the Satellite Book Club, Office of the Chief Learning Officer, and the GOZAR and JPSS programs. Without further ado, I'd like to introduce Dr. Mike Pavolonis, physical scientist, NESDIS, Madison, Wisconsin. He leads a science team focused on utilizing artificial intelligence and other techniques to transform large volumes of environmental data into actionable information. Product systems developed by his team include the ProbSevere model, Fog and Low Stratus, which just went into operations, and VOLCAT. Dr. Pavolonis also serves as the NESDIS lead for wildfire product planning, coordination, and user engagement. And this is Mike's second time here joining us at the Satellite Book Club. Mike, welcome back.
Thanks, Jordan. Good to be back. This is a great venue to present. I realize this topic is maybe a little bit, it's sort of in the specialization realm. It's not broadly applicable to a lot of problems that forecasters in the National Weather Service encounter more frequently. But I will try to tie the volcanic hazard problem into some other application areas that are more commonly observed, such as fires, because there is some synergy there. So I am going to talk about the Volcanic Cloud Analysis Toolkit, which I'll tell you a bit more about here at a very high level. So VOLCAT is essentially a collection of AI type tools that try to address the volcanic cloud problem from starting with early indicators of new eruptive events, going to detection of new volcanic clouds, automated tracking of volcanic clouds, characterization of those clouds, and then helping to inform the models and initialize the models that are needed to forecast the dispersion and transport of volcanic constituents in the atmosphere, most namely volcanic ash. The observational data is largely driven by satellite data from both geostationary and low Earth orbit satellites, a variety of them, but it also integrates some non-satellite data. For instance, ground-based lightning is a very useful data set for detecting and characterizing some more significant explosive volcanic activity. So volcanic clouds are part of the NOAA mission set. So NOAA operates 2 volcanic ash advisory centers, 2 of the 9 that exist in the world. And these volcanic ash advisory centers exist because volcanic ash is a major aviation hazard, as most people know by now. One of the volcanic ash advisory centers operated by NOAA is within the National Weather Service in the Alaska region, within the Alaska Weather, the Aviation Weather Unit, sorry, screwed up my acronym there. And the other one is actually a NESDIS within the Satellite Analysis Branch. And you can see the 2 regions of responsibility. The Washington VAAC has a large region that spans the continental United States down into Latin America, and the Anchorage VAAC has a large area up in the North Pacific. We have close collaboration with the both of those VAACs in terms of the development work that we do is closely tied to the user needs. And so we actually have an initiative that the JPSS program funds where we work very, very closely with the Anchorage VAAC, Jeff Oshinsky being the primary person up there, and Jamie Kibler in the Washington VAAC as well. In addition to Volcanic Ash Advisory Centers, NOAA operates several meteorological watch offices with SIGMETting responsibilities, including the Aviation Weather Center, the AWU, and the Pacific region. So there's broader interest in this beyond the Volcanic Ash Advisory Centers. The Central Weather Service Units, or CWSUs, of the Weather Service also have an interest in this. And we have lots of ongoing collaboration with other Volcanic Ash Advisory Centers because there's a lot of coordination that goes on between VAACs, because ash clouds will often cross VAAC boundaries, and coordination being very important. So if you look at sort of the typical, if you sort of standardize the VAAC workflow, it looks something like this. And the way the workflow goes is dictated by standards and practices set by the International Civil Aviation Organization within a document called Annex 3. So you have the detection of new volcanic events, and there are some requirements in terms of the timeliness of that detection. You have to, presenting where the volcanic ash is in the present and at what height it is, and then where will it be in the future. And then, of course, there's value-added things that VAACs do all the time with their customers. So a big thing I want to point out here is that the first three parts of this workflow are going to be changing in a really significant way sometime in the 2020s. So the VAACs are going to be going, the ICAO standards are shifting such that the VAACs will go from providing polygons that capture the ash cloud and its height in the atmosphere to more like a four-dimensional data cube of ash concentration. So 4 dimensions, the 2 horizontal, the vertical, and time. That's a very, very different paradigm and a very challenging paradigm to meet. And so that is one of the main drivers of the work that we're doing in development. And so the most, all of this workflow, every component of it is important, but the first part, kicks off the entire thing. So we've spent a lot of time and effort on getting better at automatically detecting eruptions. And, just like every other application, this new generation of satellites, the GOES-R series, JPSS series, detection of volcanic eruptions has gotten much, much better. But like every other application, the data volumes have grown, and the data overload challenge is present and something we have to deal with. So one of the things that we looked at is we made a very conservative estimate as to how many new satellite images each Volcanic Ash Advisory Center would have to look at. Again, a very conservative estimate of each day in order to get complete coverage of all of the volcanoes in their region. So assuming that a volcanic event can happen at any one of their volcanoes, how many images would they have to look at per day? A very conservative estimate. So if you look at the Anchorage Volcanic Ash Advisory Center, they would have to analyze over 1,000 new images every single day, new satellite images. So that amounts to about 1 new satellite image every minute. If you look at the Washington Volcanic Ash Advisory Center, which has a larger area of responsibility, you would be looking at over 6,500 new satellite images per day, which amounts to 1 about every 15 seconds. So obviously, humans are very good at picking out things in satellite imagery, and humans will always do that job. But the one thing that is very challenging is to keep up with all of the new data coming in. And so we put a lot of time and effort into automatically detecting volcanic eruptions, and identifying new eruptions, and then providing that information to users, which was not a trivial task. This is a very complex problem. And then on top of that, being able to distinguish between new eruptive events and clouds that are dispersing from past events. All a very challenging thing, but we have put together successfully a collection of artificial intelligence algorithms that allows us to put out a product and service like this. So this is the VOLCAT event dashboard. It's a web-based dashboard that captures new volcanic events within a time window defined by a user. You can customize your dashboard. You can customize it by the region that you're looking at. You can customize it by the time window that you're looking at. But all new volcanic events automatically detected in satellite imagery, regardless of what satellite it is, get posted to this dashboard. So new volcanic event could be a new ash emission, could be a new sulfur dioxide emission. It could be a spike in thermal output from the volcano or new thermal activity at a volcano. But it all gets posted to this, and I'll sort of just walk you through in a moment how these different pieces work. But it's become sort of a mainstay in VAAC operations and as well as within other user groups such as airlines. So, you know, VOLCAT is routinely cited within volcanic ash advisories. I think at the Washington VAAC alone, it's been cited over 7,500 times in the last few years in volcanic ash advisories. We know airlines rely on it to make strategic and tactical decisions. This is just from the Delta Airlines Met Department. Even Bernie Sanders in the background seems to be excited about it. I'm not sure what I think this was from 2015 or 2016. So, all right, I'll walk you through a little bit of the dashboard here. So for each of these events, there's a drop down, and you can, there's 3 different buttons currently that you can click. One is alert detail. So when a new event is detected, an alert report is automatically generated. And you can go to that alert report, which includes information on the source volcano, some important metrics, how high was the emission, things like that, as well as images that allow a user to assess the quality of the alert. Is this a real thing? Is this something that requires action or not? There's also a link to routine imagery that's centered on volcanic arcs of interest, where we compile all of the images from all of the different sensors, as well as quantitative information and ability to interact with the images, including generate polygons. And then there's the thermal dashboard, which characterizes thermal output in the form of radiative power, similar to what's done for fires, at volcanoes that have such activity as a function of time. And so I want to say a little bit more about this one because it relates to other application areas, namely fires, which may be of broader interest to the group listening here. So one of the unique capabilities we have in detecting and characterizing thermal output or radiative power from volcanoes is that the technique that we utilize accounts for cloud cover, which allows us to put together a coherent time series of radiative power and have more consistent detection. So one way to prove how this works is you can take real satellite imagery with all of its complexities, and you can insert a volcanic or a thermal anomaly, doesn't matter what source it is, be volcanic, non-volcanic, you can insert a thermal anomaly of a known power output into the imagery, and then I'll allow it to evolve and then apply your retrieval to it and see if you're able to replicate the power output that is known. So we did this here. This just happens to be, so what you're going to see here is we inserted a 100 megawatt anomaly into a Himawari 8 satellite image at this volcano called Todoku Ranu, which is inactive and doesn't have a real anomaly. And we looked at a 24-hour period here. So the yellow line is the 100 megawatt power level, the truth. The red is the retrieved radiative power by the algorithm. And then the green just shows you how the background long wave brightness temperature evolves, showing you, it basically indicates clouds move in and out, the surface temperature, the background temperature changes. But what you can see here is that the retrieved power, it's a little offset from the true value because it's retrieved using an empirical relationship, but it pretty closely matches the true value, even though there are clouds moving in and out. So it sort of demonstrates how this works. So you can imagine that this is helpful when you're monitoring fires, because you can get clouds that move in and out, you get pyrocumulonimbus, you get thick smoke clouds, things of that nature. So I'll just show a radiative power time series for a couple-day period here from the East Troublesome Fire using the same technique. So what you're going to see is the radiative power is in red in watts. So when you're above 10 to the 9th, that's a gigawatt. And then top is multispectral imagery. This is all from GO16. And that just shows how the anomaly evolves in imagery. This imagery includes the midwave IR, so it's very sensitive to thermal anomalies. The white overlaid is where the automated algorithm, the bounds of where it detected the anomaly. And you can see here how the radiative power evolves in a way that is consistent with the presentation and the imagery. The green lines is an estimate of the atmospheric transmittance, which sort of, when it's smaller, it indicates when there's more cloud cover present. But what you can see is that you can get these very coherent time series, not perfect, but coherent time series under complex conditions. And we spent a lot of time and effort doing this for volcanoes because volcanoes are very cloudy places. But this technique is also applicable to the fire problem. And the dashboard concept and the alerting concept is also applicable to the fire problem. So we have some prototyping going on right now. This isn't going out to users or anything, where we're setting up similar dashboards to alert for new fires, and also thinking about how we would set up dashboards for monitoring radiative power over time, this by event, similar to what we do for volcanoes. Okay, so I want to wrap this up so we have more time for discussion. So in summary, there's a lot of ongoing research continuing. I mentioned the changing ICAO requirements for volcanic ash. That means we have a lot of work to do in terms of getting the VOLCAT capabilities linked in with other capabilities that are needed to meet those requirements, especially the dispersion modeling through the high split model. We're looking also at sulfur dioxide as an aviation hazard, and looking at some more value-added products such as time series of volcanic cloud properties. We have a project ongoing right now to transition VOLCAT, which currently runs in an experimental mode at the University of Wisconsin, to the NESDIS Common Cloud Framework. I've hinted at that there are collateral benefits here, although VOLCAT was initially geared towards volcanic applications. There's a lot of synergy with other applications. Looking at lava and looking at fires from a radiative transfer perspective is pretty much an identical problem. You could say the same thing for ash and dust in the atmosphere. I didn't talk about dust, but there's synergy there as well. One of the major lessons we've learned in doing this work over the past 10 years is that, higher order products are more effective way to exploit environmental data when you're talking about decision support. So a lot of what we do with satellite products, if you look at the satellite product catalog, it largely, not exclusively, but largely consists of geophysical parameters. Those geophysical parameters are useful, but they generally require additional analysis or processing in order to make them applicable, directly applicable to decision making. So what our focus area has been is on products that reside closer to that data decision-making interface, and sort of VOLCAT is constructed with that in mind. I'll just end with this animation of the Mount St. Helens eruption, courtesy of the UW Sims blog. And I want to note that this entire effort is the result of a very large team of scientists collaborating, and very much as well as engaged users that you see listed here. So thank you. We're happy to have discussion now.
Thanks, Mike. Steve, are you there to lead the Q&A?
Yeah. Hey, Mike. How do you envision VOLCAT moving forward? Because it's very impressive. How do you envision it moving forward within the Weather Service with respect Is it possible to get it into AWIPS, or will we use a web-based system in AWIPS just to view VOLCAT?
Yeah, that's a good question. So right now we don't have a linkage into AWIPS, but we're very AWIPS aware from other projects and from just years of working this problem. So we do have we have some initial discussions going on with the groups doing that AWIPS development to figure out the best way to get VOLCAT into there. VOLCAT is event driven. So, you know, it's one of the ways it distills the large volume of data is by extracting things that are of interest and throwing everything else away that aren't of interest. And so instead of throwing, you know, a whole bunch of data where 99% of it isn't meaningful at users, we're extracting, you know, whatever, the small percentage that is meaningful. And so how do we set up a paradigm where we're only pushing products to AWIPS when there is an ongoing event? You know, that's a different paradigm than what we normally do. So that's why it requires some additional thought and development efforts.
Yeah, and I guess one of the real, you know, doing event-driven stuff in AWIPS is a different paradigm. And how do you see collaboration taking place with humans? I mean, because you're using great artificial intelligence algorithms now, and you're trying to deal with data overload. How do you envision human beings being involved in the process and adding to AI because of human ability to be creative and see things that AI may not be able to?
Yeah, absolutely. So the way we've designed, the way the AI and the human interacts are, you know, it sort of preserves that unique human contribution. So, you know, the AI finds features of interest, and then it packages them up, the post-processing on top of that, packages that up in a way that delivers it to the user so that the end user still has the final say in whether or not what action, if any, needs to be taken. And we don't see that changing at all. It's still going to be the Volcanic Ash Advisory Centers, the meteorological watch offices, the CWSUs, the humans making the final decisions. But what we're doing is just trying to provide higher level support for those decisions so that, you know, they're made more efficiently, and it frees up the humans to do things that AI can never ever replace, such as interacting with the stakeholders and adding value that way. So the humans will always have the final say. This is just sort of a force multiplier for what the humans do.
Great. One of the folks in the audience has a request that you display your summary slide again for a few seconds.
Sure.
So,
okay.
Steve, this is Jordan. If you don't mind, I can jump in with a question for Mike here.
please.
Yeah, Mike, thanks. Since coming over to the Weather Service, I've met a lot with our different mission service areas. And one of the mission service areas that I met with recently was the tsunami mission service area, which traditionally we've not been able to use satellites very well to help in the detection of tsunamis. However, as we are in our planning process for GeoXO, we did our due diligence and talked to them about the possibility of detecting coastal inundation in some kind of automated sense. Of, you know, can we use satellites, for example, to detect very subtle changes in where we might have coastal inundation in certain areas where coastal elevations are fairly low. I guess the question for you is, have you thought about how we can, in the future, use these kind of automated algorithms to drive where we're positioning satellite mesosectors and helping to make these kind of detections at a full system level, where where we notice something that might require more interrogation, we not only alert the user, but we build in systems into the satellite to scan more frequently there, or in a more fuller range of spectral bands if the satellite allows that capability.
Yeah, Jordan, that's a good point. So, I mean, this type of automation does lend itself to helping with satellite tasking, whether it's, the scan mode for a geostationary satellite, or it's, acquisition of unique data from low Earth orbit. This does provide a mechanism for helping that, and there's one thing actually we're proposing to do now in collaboration with NASA. So NASA has a proposal that they're putting together, a NASA team, for a new LiDAR constellation in a unique orbit. And the LiDAR will have the ability to point off nadir. And so one of the goals of the mission is to help with volcanic clouds. It has many other goals as well, but one of the points of discussion right now is how we would use VOLCAT to automatically inform the mission support folks, should this mission go forward, when they would want to point the laser off nadir to capture a volcanic cloud, when that opportunity arises. If we're just relying on sort of scientists or humans finding interesting cases, just happening to stumble upon them, we're not going to realize all those opportunities. So I think, yeah, absolutely, more of this can be done, especially as we get more flexible satellite assets.
Mike, there's another question concerning the fact that some of the other products you work with are probabilistic. And I think you've done an excellent job with VOLCAT, just trying to assimilate all this data and come up with a detection. Is that how you view VOLCAT at this point, is handling huge volumes of data and trying to get an identification of a volcanic event?
Yeah, that's a big part of it. But then once a new event is detected, there's automated tracking that's in place, and there's characterization of the cloud. So the satellite has ability to some extent to estimate things like the height and the loading of volcanic ash and sulfur dioxide and some microphysical parameters. So, one of the big areas of emphasis right now is how we take all of that information and automatically or develop an automated workflow that connects it to the models that will forecast where the cloud will be in the future and what its properties will be in the future. So we have a lot of ongoing work with the ARL high split group right now, because high split is the main tool for doing that in NOAA. But that's, I think we've spent a lot of time on the initial upfront detection. We're happy with where that's at. There's always room for improvement, but now our focus is shifting to the forecasting part of the problem more and more.
Thank you. Have you been in contact with any of the other volcanic ash centers around the world? Are they interested in what you folks have been doing? And do they want to buy the system from you and make millions of dollars?
Yeah, we do have lots of collaboration with other Volcanic Ash Advisory Center. So actually, the Japanese Meteorological Agency, they operate the Tokyo VAAC. We've provided this software to them, and they utilize it in their operations. The same thing goes for the Bureau of Meteorology in Australia. They operate the Darwin VAAC, and the Wellington Met Service, the New Zealand Met Service, which operates the Wellington VAAC. They also run VOLCAT operationally. They run it within the AWS cloud, actually. So you know, the reach of the system is fairly far, and every other VAAC uses our web interface to get at the products as well. So yeah, we have some form of collaboration with every other VAAC. So all 9 VAACs to some extent utilize this.
Okay, yeah, thank you, because that's, you know, at AWC where we're working, we're putting out advisories or SIGMETs for volcanic ash if it moves into our area from AWU in Alaska. And a lot of times what we see is volcanoes, they wait for just after we transmit our products to erupt. And so we always end up having an issue with we'll put a volcano on the map, or we'll take one off in collaboration with folks around the world, and then a volcano will erupt, and then we have no way to modify, or, well, we can correct and send a whole new package out. But I think it would be interesting, now that you've mentioned that you are interacting with all the other VAACs with your software, that this is a really great opportunity to help us as to improve our decision support worldwide, because we're sending information out worldwide, and so that'll be a nice way to integrate your stuff with us, and so we can include that as part of improved decision support at the Aviation Weather Center, because we're one of the world area forecast centers with WAFC London. And so we're trying to we're issuing maps 4 times a day, and now we're going to start doing it also 4 times a day, but with every 3 hours after 36 hours. So there is a new opportunity to improve our IDSS support for that. And I was wondering how you feel about trying to integrate it further into the decision support for different parts of the Weather Service and internationally through ICAO.
Right. Yeah. Yeah. We're always interested in making the information more useful to more people, and so, you know, I'm connected to the ICAO world through there are some expert groups that the World Meteorological Organization sponsors that advises ICAO on, you know, matters related to volcanic ash and of that nature. So I've been involved with that process for over 10 years, and so, yeah, I'm happy to, I know the lay of the land fairly well, and I'm happy to take suggestions from AWC on how we can better coordinate.
No, yeah, thank you very much for that, because that's something that we're there's a whole new opportunity now, and so this is really great for us to work with you and the rest of the world, because there's a lot, you know, even though there's COVID and air traffic is down 50 to 70%, it's going to come back. And as far as I know, the volcanoes will probably still erupt. And so this is a great opportunity for us to work together and the whole world to improve decision support for that. So I look forward to having an opportunity to working with you and your group, and actually not just me, but AWC, and bring something like VOLCAT into our test bed and to work together to help improve decision support and come up with new ideas for new products.
Yeah, absolutely. Yeah, we're happy to have that discussion and pursue that.
Hey, Mike, this is Wayne. Speaking of collateral benefits, have you seen any events lying outside ash, dust, and volcanic ash, such as the Libya explosion?
Yeah, we've seen explosions. We've seen meteorites, the debris from meteorites. We've you know, there are relationships here to smoke plumes as well, especially thick smoke plumes. So there is some overlap in the, you know, in that space. You know, our main focus is on the volcanic cloud part, but we developed the software in a way that was mindful of the fact that there is synergy with these other applications, and that's why we were sort of able to to sort of spin this off and try to flush out some new capabilities for fires, because we developed the software in a way that allowed that to happen.
Hey, Mike, Becca's got a question. How will we be able to integrate VOLCAT into the AWIP's Hazard Services program and that software? I mean, it's going to take a lot of work and integrating, but do you see it moving that way?
Yeah, I do. So I think Dan Neufield's on this call, and you know, Dan has reached out regarding this, and so we're trying to sort of flush out. We're at the initial stages of just trying to flush out exactly how we'll do this. You know, this is going to be in a cloud environment, and so there's, you know, there's a lot of unique aspects to this compared to how we traditionally do operational product generation in NESDIS. So, you know, I don't think there will be any major technical hurdles. It's just getting the work done.
Yeah, I agree. You've built an excellent platform, and actually you're finding out now, I mean, and you've already known this, that there's loads of applications. And so this is really terrific. I may have missed this in your presentation. How well are you able to forecast the thickness or the depth of the volcanic ash layer?
Well, it's difficult to forecast because it's difficult to observe. We don't observe that directly unless you're fortunate enough to have a LiDAR observation that can vertically resolve the ash. So, you know, how well it can be forecast, it depends on what you assume is the initial state. So you have to make some assumptions about either how the ash is coming out of the volcano, or if the cloud is detached from the volcano, where it is initially and what its initial state is. And then on top of that, you have, you know, you're at the mercy of how good your wind fields are that are moving the ash around, and how well the vertical profile of wind is resolved at both direction and speed. So it's a huge challenge. What we've seen from LiDAR data is that typically for dispersed ash clouds, they tend to be on the thin side, 1 kilometer or less thick more often than not. So that's, you know, it tends to organize in a lot of thin layers, and how well you can resolve those layers with modeling capabilities, I think it depends on where the cloud is. If it's in a very dynamic environment with a lot of vertical wind shear, such as in the mid to high latitudes, you can do a pretty good job with it. If it's in a tropical environment where the wind fields are maybe it's, you know, it's more barotropic, and the model wind fields are perhaps have a greater amount of uncertainty, that becomes even more difficult. So having a way to do this consistently for every volcanic event, regardless of where it is in the world, is a challenging task. And one of the concerns that we've had is that a little bit too much emphasis has gone on the reanalysis of the Eyjafjallajökull eruption in Iceland, which occurred in a very baroclinic atmosphere with a lot of wind shear that was pretty well resolved by models, but not a lot of thought has gone into how do we handle, how do we provide a service, that more sophisticated service in situations that are more complex, such as tropical eruptions.
Okay. Thank you so much, Mike, and thank you, Steve. Really appreciate your presentation and a lot of the discussion that ensued. I think it was very productive and a great presentation, a good topic to be discussed. We will post a link to the feedback survey in the chat. Next week, I hope you're going to join us Thursday, November 5th, once again at 12 noon Eastern Time. Wang Meng, physical scientist at NESDIS STAR, will present on radar and satellite blended snowfall rate product and its applications. Look for an email from the Tower S team. David will also post a link there in the chat room so you can add it directly to your calendar if you'd like to do that. Without further ado, please feel free to tune in tomorrow for the Tower S update if you're a Weather Service field site. That'll be Friday, October 30th at 1 p.m. Eastern for the latest of products available in the field. Otherwise, I hope everybody's staying well. We'll talk to you next week. Thanks, Mike. Thanks, Steve. And thanks, everybody, for joining us.
Yeah, thanks, George. Thanks, Steve.